Hey guys, this is my video on the derivative, which is an operator in calculus, and it's going to be very important in this course. So first of all, I've got a graph of some arbitrary function f of x. I've got the x-axis, the f of x-axis, and then I have 2 points on the x-axis labeled. I have x1 and x1 plus h. And they are, of course, separated by a distance h. So first I'm going to plot the points x1, comma f of x1, and x1 plus h, comma f of x1 plus h. So now I want to find the average rate of change of f of x between x1 and x1 plus h. So to do that, I'm going to start by drawing a straight line between these 2 points. And then I want to find the slope of the straight line because slopes are a rate of change. So to do that, I'm going to get a slope triangle over here. Okay, now this side is h. And this side is f of x1 plus h. So f of x1 plus h minus f of x, right? It's the difference in height between these 2 points. So my average rate of change is going to be f of x1 plus h, but I'm actually going to generalize this. So instead of having x1, I'm just going to write x. So this will work for any 2 points, x and x plus h, which are separated by a distance h. So any 2 points separated by a distance h, the average rate of change is f of x plus h minus f of x, all of that, it's delta y over delta x, so all of that over h. So our average rate of change formula, sometimes called the difference quotient. Okay, so now I'm going to draw another f of x. It's going to be another just arbitrary function. My axes, I've got my x-axis, f of x-axis, and then just some other arbitrary function right there. And now I will label my new x1 right around here. So what I want to do with this is I want to find the instantaneous rate of change at x1. So here's x1 on the graph, x1 comma f of x1. To find the instantaneous rate of change, you're going to see this line. It's called the tangent line. It's a line that just touches the function at that point, and that's called the tangent line at that point. And the instantaneous rate of change is going to be the slope of this tangent line. You can kind of see how that one makes sense. So how do we do this? Well, we can see from our difference quotient that we are going to get this by having h be really, really small. The closer h gets to 0, the more exact our answer is going to be. So we would ideally like h to be equal to 0. However, h can't be 0, it's in the denominator. So we're going to have to use limits. So the limit is h approaches 0. That means we get a more exact answer the closer h gets to 0. Limit is h approaches 0 of f of x plus h minus f of x all of that over h. The limit is h approaches 0. That is the instantaneous rate of change at some value x. Again, I generalized this to x instead of x1. And that we are going to call the derivative of f of x. So it's d by dx. This is how we denote the derivative of f of x. That's all the derivative is, just the instantaneous rate of change. And we can also, as a shorthand, we're going to call this f prime of x. F prime of x. And this prime is sort of like an apostrophe. It looks like that. And this is our definition of the derivative. And the derivative of something like f of x is actually a function. And we can graph the derivative over here, not a straight line. There we go. So we're going to graph f prime of x. Going to be our x-axis. Okay, I'll just fix up this graph over here. Okay, so to graph this, we're going to have to find a few important points. So let's start with where the derivative is 0. That's going to be at any relative minimum or relative maximum, or sometimes the graph will just show up flat. And that is also where the derivative is equal to 0. We draw these tangent lines. You notice that these tangent lines at the relative maxima and the relative minimum are all have a slope of 0, so the derivative is 0 at those points. So you can just ignore the x1. We don't really need that anymore. Okay, so we plotted where our derivative is 0. Over here it starts. It looks like it's a little bit positive. Then it looks like the slope gets a lot more positive, and then it goes down to be 0. So it's gonna look sort of something like this. Go down to get to 0, and then the slope goes negative. Comes back up to be 0, and then it's positive again, same kind of thing. It's really positive, and then it goes back down to 0, then the slope ends up being negative. So this is it's a rough sketch of f prime of x, but that should sort of make sense. It looks like a pretty good representation of f prime of x. It's not exact, but it's pretty good. Okay. So next, I am going to talk about the second derivative. So, pick a new color for this. Nice orange. So, the second derivative, d squared by dx squared, this is how you denote the second derivative of f of x. We can denote this as f double prime of x, or f prime prime of x. And of course, you can generalize this whole thing to the third derivative, the fourth derivative. Usually, especially in quantum mechanics right now, we're going to be dealing mostly with first and second derivatives, not third. But you can see how this would generalize. It would be f prime prime prime, and that would be the derivative of the second derivative. So the second derivative is the derivative of the derivative, du by dx of d by dx f of x, which is f prime of x. So the derivative of f prime of x, the derivative of the first derivative, is the second derivative. Take the derivative again, you get the third derivative, d cubed by dx cubed, etc. So that is our definition of the second derivative. We could also graph the second derivative function if we wanted to, where we would see the second derivative is 0 here, here, and here. And then we'd just do the same thing to graph it. I'm not going to do that right now, but if you would like to, you can definitely do that. It's not super hard. And yeah, so this is the definition of the derivative. Second derivative is just our difference quotient. You should really know these. These will be really important. And now we will talk a little bit about the rules of taking a derivative. And this is not a full, complete description of all of this. There are definitely a ton of rules. I'm not covering that many rules, actually. And I will have links in the description to more. This is just what you really, really need to know. And even some more complicated stuff will appear in this course, but I'm just kind of covering the bare minimum. Okay, so now let's move on to derivative rules. And when we do this, I'm just going to have a note up here. C is a constant. Underline that a few times. Remember, it's really important in these rules we know that C is a constant. And in that we'll see, you'll see where C appears after this. Okay, so our first rule is going to be called the constants rule, where the derivative, d by dx, of c, the constant c, is equal to 0. That should make sense. The derivative is a rate of change, and the rate of change is a constant is 0. A constant doesn't change. Okay, so next is the constant coefficients rule. So d by dx of c is going to be all the argument of the derivative, c times f of x, some function f of x, is equal to, you can take the c out of the derivative term, this is going to be c times f prime of x. So that is our constant coefficients rule. Okay, so next we can take the derivative d by dx of the function e to the cx. And this is equal to c times e to the cx. And note, if c is 1, that's the derivative of e to the x is equal to 1 times e to the x. So e to the x is its own derivative, and then its own second derivative, third derivative, etc. It is the only function to my knowledge that does that. Okay. Now, finally, the sums rule. So d by dx of, you can call it a plus b, doesn't matter if they're functions, constants, whatever, anything a plus b is equal to d by dx of a plus d by dx of b. And that is, you could also write that as a prime plus b prime. This is called the derivative being linear. It sort of distributes here. So the derivative of a sum is equal to the sum of the derivatives. You can also see that this can be generalized to a sum of 3 things, a sum of 4 things, or even an infinite sum of things. A sum of infinite things, it's an infinite sum of the derivatives. And you will see that will make sense eventually, and we are going to do that, take the derivative of an infinite sum in quantum mechanics, and it's very important to know that that is equal to the derivative to the sum of the derivatives of each individual term that we're summing up. Okay, so now we can use a few of these at a time. So say we are taking the derivative, or actually the second derivative, d squared by dx squared, d squared by dx squared, not great d. D squared by dx squared of e to the cx. What is that equal to? Well, that is the derivative of the derivative. So it's d by dx of the derivative of e to the cx, which is c e to the cx. We can then, using this rule, we can take the c out of there, take this derivative again, we get c times c e to the cx, which is c squared e to the cx. And note that this derivative exactly is going to be very, very important in quantum mechanics. We are going to use this derivative precisely. Okay, now, finally, we can use partial derivatives. I'll switch to a new color for this. And partial derivative is going to be this curly d by dx. And all this does, it is the same as an ordinary derivative. It works the same way. However, the only difference is that it can act on a function of more than one variable. It can act, say, on a function of x and a function of time. Now, what this does is if you act on g of t, function of time, this considers time and any function of time to be constant, or just the time component of the function of time. So this is going to be equal to 0. Right, so the partial derivative of a function of time is a partial derivative with respect to x. We have to be very careful when we talk about partial derivatives. We have to say what variable they're taken with respect to, and you should usually do that with a derivative, the derivative with respect to x. But this is the partial derivative with respect to x of a function of time. That's equal to 0 because t is considered a constant. This partial derivative just makes any variable other than x constant. So we can see the partial derivative d by dx, partial derivative with respect to x of f of x times g of t, that's going to be equal to, you can, this g of t can be treated as a constant, you can take that out of there, and that is g of t times f prime of x. So in quantum mechanics, for example, when we deal with a function of x and t, we'll have the function psi. This won't make sense to you right now, but it will eventually. We'll have a function of both position x and time t. And so when we're taking the derivative of it, we have to take the partial derivative. And that's going to consider t a constant if we're taking the partial derivative with respect to x, or it will consider x a constant, because we can also take the partial derivative with respect to time, ddt.